4 o'clock. I think we're going to go ahead and get started with our final exam review. Wow, this is the last time I will be hosting any SI review for 240. I know, isn't that sad, right? Well, anyways, we want to make sure you all succeed on this final exam. I'll say a couple things about the final exam before we jump into its review. So first of all, the final is generally easier than the 4 tests that precede it, which I'm sure you will all like. Dr. Raven is going to be focusing on larger picture themes that she wants you to carry over to future biology classes. She's probably not going to ask you what protein charges tRNA molecules by attaching an amino acid to the top of them. The answer is aminoacyl tRNA synthetase, if you remember, but she probably won't ask something like that. She'll probably ask you something like, where does tRNA initially load into the ribosome? You got to go, oh, that'd be the A site, right? Well, yeah, don't worry, we're going to cover all this. Note about this session, so this is my Grand Slam finale SI session. It's going to be 3 hours long, but we're going to take a break in the middle. So after an hour and a half, we're going to take a little 10-minute break. You can stretch your legs, get a snack, get a drink. So you don't need to worry about that. Also, I have 2 blank pieces of paper coming around. If you could write your name and student ID on them, just keep passing those around. Every SI leader has their exam review today, so it's crazy at Reach right now. All the sign-in sheets are gone, so I had to use these blank pieces of paper. All right, yeah, emergency, siren, right? Final tomorrow. I hope you all reviewed your old tests. Those are very helpful in predicting what will be on the final. And without further ado, I suppose we could just jump right in to everything we need to know about the final exam. Yeah. So I'm just going to tell it to you if that's okay. I'm just going to tell you exactly what all this stuff is. I'm not going to go asking around. I'm just going to breeze through it. Sound like a plan? Yeah. And then I have the live stream going, so if at any point you want to go back and review what I said, you are more than welcome to do that. The link works even after the review ends. It's on Blackboard. Okay, so we started off talking about matter. Matter, what's the matter, right? So basically everything in this universe is made up of matter. Matter is composed of elements. Now, biologically relevant elements are called our essential elements. Anyone remember what the essential elements are way back from day 1? CHOMPs, yeah. CHONPS. These are our essential elements. These account for over 90% of all living matter. So we have here carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are going to be our essential elements. We also have our non-essential elements, also known as trace elements. Those are going to be any other elements that are necessary in a living organism that are not necessarily ubiquitous to life. So our trace elements, for example, iron is a trace element in humans. We need iron to survive, right? That's how our blood finds oxygen. If we didn't have iron in our systems, we would die. It's a trace element, but it's necessary to keep us alive. Do all living organisms need iron? Not necessarily. It's not necessary to sustain life. So, a single-celled eukaryote at the bottom of the ocean doesn't necessarily need iron, but every living organism needs these elements. That's why they're essential. Trace elements are still necessary for life in the organisms that they are present in, but not necessarily ubiquitous to all living organisms. They're going to be our trace elements. Okay. Now let's talk about the makeup of some of these elements. This is sort of like the chemistry part, the chemistry behind life. So we need to know the anatomy of an atom. This should be a pretty basic review. Most of you are in Chem 201 right now as well. So we have this sort of core. What is this core called of our atom? Nucleus, not to be confused with the cell's nucleus. So we have a nucleus. Nucleus is made of protons and neutrons. Protons have a what charge? Neutrons have a charge, and electrons have a negative, that's right. And our electrons orbit around our nucleus, kind of like how the moon orbits around Earth. So these electrons are all flying around this nucleus. Where do we get our atomic mass from? What is the weight of this nucleus? How do we calculate that? Protons and neutrons, that's right. So if you want to find the weight, the atomic mass of any element, all you do is you add up all of the protons and all of the neutrons. Electrons are effectively weightless. So if you, I should probably talk about this too. For every proton, there's usually 1 neutron. So if I give you an element like helium, is what I drew here, we know helium has 2 protons. It must have then 2 neutrons as well, under normal conditions. Now, there are wonky types of elements called isotopes. isotopes have a different number of protons and neutrons. So an isotope of helium would be helium would say a third neutron. We're still helium. The element is identified by the number of protons it has, right? If you add more protons, then you don't have helium, you have a different element. Protons define the element. If you add more neutrons, though, we just have helium, but a heavier version of helium. That's going to be a helium isotope. What would be the atomic mass of this helium isotope? What's atomic mass again? What plus what? Protons plus neutrons. So if you want to find the atomic mass of something, add up the protons, add up the neutrons, and you have that atomic mass. The atomic mass of this helium atom right here, this helium isotope, would be 5 then. So you'd say 5 moles per gram, but don't worry about that unit. Okay, so we have our atomic number and we have our mass number. They are similar, but a little bit different. Let me pull up a periodic table to show you what I mean. Periodic table. So Dr. Raymond could hypothetically give you something from the periodic table and expect you to figure out its atomic number, its atomic mass. Oh, come on, load a little faster for me. Periodic table. Periodic table. Why is it so hard to find a periodic table with atomic number and atomic mass? Modern periodic table. This looks promising. Don't worry, we have 3 hours, so we're not wasting too much time. I actually predict we're going to end a little bit early because I usually breeze through this in 2 hours historically, the past 2 times I gave this review. Okay, let's be more specific. Okay, let's look at this periodic table right here. Can we all see this periodic table? Can you all see the number up there? Good. So our atomic number, look up there at iron. See, we're going to use iron as our example. So iron, its atomic number is 26. That means that it has 26 protons. Any element that has 26 protons will always be iron. If you look at, say, carbon, you can see carbon in the top right has 6 protons. Any element with 6 protons is always going to be carbon. If we want to look at the atomic mass of carbon, we know for every proton, there is a neutron, right? So we go, okay, all the protons plus all the neutrons, 6 plus 6 equals 12. That's the atomic mass of carbon. There are some variants of carbon, though, that have different numbers of protons and neutrons. Those are called isotopes. If you have a carbon with 6 protons and 7 neutrons, you get an atomic mass of 13. That's going to be a carbon isotope, right? So remember, neutrons can change in isotopes, but if you change the number of protons, you're actually changing what element you have. I don't want to beat that to death. Is everyone kind of good on that? Yeah, if there's any confusion, feel free to stop me because, again, we have more time than we need. Okay, so we talked about atomic number and mass number. Ooh, types of bonds and electron sharing and non-sharing. So let's talk about some of the bonds that we see. Okay, so we have a lot of major classes of bonds. Can someone tell me some bond types? Anyone? Someone tell me their favorite bond type. Yeah, what's your favorite bond type? Covalent. Covalent, that's a good bond type. What's another bond type? Hydrogen. Hydrogen, that's a good bond type. What's another bond type? Yeah. Ionic. Ionic, yeah, that's a good bond type too. Any other bond types? My bond type? Single bond? Huh? Yeah, double bond, polar, non-polar. Yeah, so let's break this down. So bonds generally involve some sort of transfer of electrons, except for hydrogen bonds, but we're going to talk about those. So we have covalent bonds, and we have ionic bonds. And then we have hydrogen bonds, which are going to be like our estranged cousin that we'll talk about later. So covalent and ionic bonds involve some sort of transfer of electrons. In covalent bonds, you have a sharing of electrons. Olivia and I are going to share markers. I'll give her my marker, I'll take hers, and then we'll trade back. I'll give her mine, she'll take, blah, blah. So covalent bond, we have the sharing of electrons, right, between any 2 elements. In ionic bonds, we have a stealing of electrons. So let's just say I want Olivia's marker, I'll just steal it. This is the equivalent of an ionic bond. So in an ionic bond, one element steals the electron of another element, And then lastly, we have our hydrogen bonds, which really rely on electromagnetic forces. So we have two types of covalent bonds, our sharing of electrons, right? We have covalent nonpolar and covalent polar. Nonpolar bonds are when you have that equal sharing of electrons. Olivia and I share our materials equally. I'm not hogging, she's not hogging. We're just totally equal in our sharing, right? That's a nonpolar bond. A polar bond, though, occurs when you have a differing electronegativity value. That's when there's an unequal sharing of electrons. That's when I keep an electron more than Olivia does. Let's do some examples. So a carbon-carbon bond is a good example of a nonpolar bond. Electrons usually exist in cloud form. So we have this electron cloud, and the electron cloud is going to be pretty evenly distributed between these two carbons. Everyone kind of see that? The electrons go evenly from both carbons to each carbon. So that's a nonpolar bond. Our polar bond usually results from something like a carbon-oxygen bond, where there's a greater electronegativity difference. Electronegativity, again, just being an element's propensity to attract electrons. Oxygen wants to attract electrons more than carbon. Oxygen has a higher electronegativity value than carbon. Oxygen's drawing those electrons more. Our electron cloud in a polar bond looks a little bit like this. It's kind of lopsided towards oxygen. So you can imagine how the electrons flow in this sort of orbit. They go over to oxygen and they stay for a long time, and then they dash back to carbon, but then they go back to oxygen really, really fast. Most of the electrons in this bond are on oxygen's side. Oxygen has that higher electronegativity value. Now, when we have polar bonds, we get partial negative and partial positive charges. Charge, again, dealing with where the electrons are located. So because the electrons are hanging out more with oxygen, oxygen is going to be a little bit more negative than it should be. That's designated as delta minus. More electrons, more negativity over by oxygen, a little more negative. Our carbon's going to be a little bit more positive because there are less electrons hanging out with carbon. We're going to call that delta positive, just a little bit more positive than it should be. This is not a formal charge. We don't have a full electron difference, but they're just kind of, minor differences. Oxygen's a little bit more negative than it should be. Carbon's a little bit more positive than it should be. That's going to be our polar bond. Now, our ionic bond involves that stealing of electrons. So you might see an ionic bond in, say, sodium chloride, table salt, right? In sodium chloride, table salt, which makes everything delicious. I bet all of you had some sodium chloride today, NaCl. What we have is sodium, Na, has this one electron, and chlorine, 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 electrons. The goal for every element is to get to 8 electrons in their valence shell. Chlorine goes, hey, I really want to have 8 electrons. I'm just going to steal your electron. Sorry, bud. So chlorine steals that electron and becomes negative, full negative. Chlorine has 1 more electron than it should. If you compare the number of electrons to the number of protons in chlorine, when it steals that electron, it has 1 more electron than it should. That gives it a full negative charge. It is a negatively charged chlorine because the charges don't balance out. Now it has 1 extra electron. Sodium over here, though, lost its electron. That means that it has more protons than electrons. It lost an electron, its charge balance is out of whack now too. So because sodium has 1 more proton than its electrons, we say sodium is going to have a positive charge. So when we have these ionic bonds, we have a charge forming. We get this negative charge on whatever steals the electron and that positive charge on whatever loses the electron. That's going to be our ionic bond. Makes charges. All right, everyone following so far? Okay, I want to make sure we understand this concept of partial charges, though, because that's where our hydrogen bonds come in. So is there any exchange of electrons in hydrogen bonds? No, there are no exchanges of electrons in hydrogen bonds. They're sneaky. That's why they're the estranged cousin. A bond without electron exchanging? What the heck, right? But it's very common. We see it a lot. So hydrogen bonds usually occur between hydrogen, surprise, surprise, and something that is electronegative or something that is more negative than it should be. So in a hydrogen bond, you usually have, say, let's take water as an example. The electron clouds in this water molecule are going to look a little bit like this. The electrons in the hydrogen-oxygen bonds are going to spend more time near oxygen because oxygen has that high electronegativity value. Does that makes oxygen delta? Okay, let me ask you again. If the electrons spend more time by oxygen, that makes oxygen then delta negative, delta minus. Oxygen is going to be a little bit more negative than it should be. Hydrogen is going to be delta positive. That's right. Do opposites attract or repel each other? Opposites Attract. That's right. So what you have in a hydrogen bond, this is what makes water so hard to boil. We'll say have another water molecule over here, right? This other water molecule is also going to be delta minus on the oxygen, delta positive on the hydrogens. This hydrogen goes, hey, I know my electrons are already in a bond, but dang, that delta negative on that oxygen looks good. So these opposite charges, the delta minus and the delta plus, are going to attract each other because opposite charges attract. There's no exchanging of electrons going on here, but there's this electromagnetic force, this force of, hey, I'm positive, you're negative, let's get near each other, right? That's going to be effectively our hydrogen bond. And when we have a lot of water molecules grouped together, we have a ton of these hydrogen bonds. Everyone understand the idea behind hydrogen bonds? Yeah? Okay, good. And then there's one other type of bond, it's just single versus double bonds. So we have single, we have double, and if you want to get crazy, we can even talk about triple bonds, but I'm not feeling very crazy today, so we won't. They're not that much different. Single bond, when there is a single pair of electrons being shared between two elements. This carbon donates an electron to the bond. This carbon donates an electron to the bond. Each carbon is giving up one of its own electrons to share with another element, right? Double bond. It's like a single bond, but each element is donating 2 electrons. This carbon donates 2 electrons to this bond. This carbon donates 2 electrons to this bond as well. That's the difference between a single and a double bond. Which one do you think is stronger? Double. Double bonds are stronger than single bonds because there are more electrons involved. All right. Everyone good on that? Okay, let's talk about some pH calculations. Remember that? That always gets people. Oh man. I remember when I gave some of my first SI sessions for this class, and people come up to me and they go, Alex, what is a monosaccharide? And I go, it's okay, you'll learn. And now we can all chuckle, oh, monosaccharides, we know what those are, right? Those are simple sugars. You know, glucose is a monosaccharide. Oh, see how far you all have come? I think it's impressive. Okay, let's talk about some pH calculations. So pH is just the measure of hydrogen ions in any solution. Hydrogen ions being H+, aka acid. The lower a pH value is, the more blank the solution is. Lower pH means more acidic. Lower pH means more acidic. Lemons have a pH of about 2. They're very acidic. The higher a pH, the more basic. That's right. So we'll have, say, pH 2, pH of 14. Higher means more acidic. Lower means more basic. Okay. So if we want to calculate pH, you might get something like this. Dr. Rabin can tell you, because again, pH is just the measure of hydrogen ions in any solution. She might say the amount of hydrogen ions, or the concentration of hydrogen ions, that's what this means, is 10 to the minus 9. What is the pH? What is the pH of this? 9. Wow, yes, it's 9. Great. We are doing pretty well. So if you are given the hydrogen ion content and you want to find the pH, all you do is go to the exponent, remove the negative sign, and that's your pH. So we're given a hydrogen ion content of 10 to the minus 9. What's the pH? Go to the exponent, remove the minus. That's the pH. That's only if you are given hydrogen ions and you're looking for the pH. We can do a similar problem. We can be given an OH minus content, also known as what makes something basic, hydroxide ion. We can say hydroxide ion content is 10 to the minus 5. What is the POH? What's the POH of this? 5. If you're given OH minus and you're looking for POH, you do the same thing as pH. Go to the exponent, remove the negative side, that's your POH. I hope you all see a pattern. If you're given hydrogen ions, you find pH. If you're given hydroxide ions, you find POH. Now, that's the only thing you can find if that's what you're given. If you are given hydrogen ion content, don't go trying to find the POH. The only thing you can get from this information is the pH. The only thing you can get from this information is the POH. Now, you might be going, but Alex, oh yeah, question.
They always have 10 to negative 14, correct?
Yes, that's right. That's what I'm going to get to now. So great lead-in, I love it. Now, you might go, but Alex, I remember on exam 1, there was a question like this. You're given a hydrogen ion content of 10 to the minus 9. What is the POH? Now, Dr. Rabin can flip it up on you. Dr. Rabin can ask you for the POH given H plus, and she can ask you for the pH given OH minus. How do you solve this? What's the only thing you can find with this information? Say it, tell me. pH, that's right. So the only thing we can find is pH. We said the pH is going to be 9. There's this secret equation I'm going to tell you that'll save your life. It's called pH plus POH equals 14. Always. pH plus POH will always equal 14. We're looking for the POH. Can't find it. We can only find pH. We find that the pH is 9, but using this wonderful equation, 9 plus POH equals 14, we can subtract 9 from 14 and get the POH is equal to 5. Everyone see how I did that? Okay, good. You can revisit it on the live stream if you would like to see that again. That's how we find pH calculations. Ooh, organic versus inorganic. Molecules that contain carbon-carbon bonds are called organic. Molecules that don't are called. Now again, note how I said carbon-carbon bonds make something organic. Is carbon dioxide organic? No. Why? Because there are no carbon-carbon bonds. This is what carbon dioxide looks like. Do you see any carbon-carbon bonds? No, there are none. So carbon dioxide is our inorganic form of carbon. Carbon-carbon bonds make something organic. All right. So that's that. Ooh, macromolecules. One word entails so much information. You have no idea. Okay. We need to know macromolecules. They're monomers, they're polymers, and the different types of them. And I am going to sprint through these. So, 4 major types of macromolecules. Someone raise their hand and tell me one type. Yes. Carbs, carbohydrates, carbohydrates. How do you want to remember it? Carbohydrates. Good. What's another type of macromolecule? Yes, in the back there. Lipids. Yes. We have our lipids. Good. What is another type of macromolecule? Yes, in the back there. Nucleic acids. That's right. Nucleic acids. And what is the last type of macromolecule? Yeah. Protein. Excellent. Protein. Good. Now we need to know all the monomers and the polymers. Let's talk about carbohydrates first. What is a monomer of a carbohydrate called? Monosaccharide. That's right. See, you don't even need me. You know this all. You know all this yourself. We have one sugar called a monosaccharide. What are multiple sugars linked together called? Polysaccharide. So if we have, say, 3 all linked together, this is a polysaccharide. What's 2 called? 2 linked together? Disaccharide. What's a disaccharide that you all know? Begins with an L. Lactose. Yeah, remember the lactoperon? We'll get to that. So monosaccharide, polysaccharide, disaccharide, those are our monomers and polymers of sugar. What is the formula for glucose? You need to know this. Good. And where does glucose fall? Monosaccharide, disaccharide, polysaccharide. Monosaccharide, that's right. On the first exam, I think like 70% of people miss that question. So glucose, monosaccharide. But I'm sure you all know that now. Okay. Well, so, oh yes, let's talk about the bonds that hold together sugars. Let's say we have this disaccharide. What is this bond that holds together these 2 sugars? What's this called? Glycosidic linkage. I'll write that out. Glycosidic linkage. So, well, actually, yeah. Okay, I'll talk about that now. So when we build polymers from monomers, there's a specific reaction type we undergo. What type of reaction is that? Begins with a D. Dehydration reaction, that's right. If you have 2 monomers, 1, 2, and you want to make a polymer or combine those monomers, you undergo a dehydration reaction. That means that you just make water and then remove water. I'll show you what that looks like. So we all know water is H2O. These 2 monosaccharides, they both have 2 OH groups on the bottom here. When we undergo a dehydration reaction, we combine these 2 OHs and we get H2O2. Makes sense? OH plus OH equals 2 hydrogens, 2 oxygens. We get H2O2. We go through our dehydration reaction. We remove H2O, and that leaves us with a single oxygen. So we combine, remove water, and then that's how we make our polymers. That's going to be true in every single one of these macromolecules. Dehydration reactions, builds up. What's the opposite? What's the opposite of dehydration reaction? What if we wanted to break this up? What kind of reaction will we do? Hydrolysis. Yes. Wow. Great. Hydrolysis. That's when you insert water in between this bond to separate it. Good. Okay. I don't want to beat that to death. So that's carbohydrates. Let's talk about lipids now. There are 3 types of lipid. What is one type of lipid? Someone tell me. Fat, triglyceride, fatty acid. Yeah. So we'll say a fatty acid / triglyceride is 1. What's the second type of lipid? Steroids, another type of lipid. And then what's the third type of lipid that we all know and love? Phospholipid. That's right, phospholipid. And let's talk about the differences between all these. So our fatty acid / triglyceride is going to look like this. This is where we store a lot of our energy. So we're going to have this thing called a glycerol group. C-E-R-O-L. We have this glycerol group, and attached to this glycerol are going to be 3 fatty acid tails. Now, a fatty acid tail is made only of hydrogens and carbons. So we have this big hydrocarbon tail. Those hydrocarbon bonds contain a lot of energy. So we are able to store a lot of energy in these triglycerides, specifically these fatty acid tails. Gasoline is all hydrocarbon bonds. Gasoline has a lot of energy. It powers your car, which is like 2,000 pounds. We have a lot of energy stored in these bonds. This is going to be our triglyceride. Our triglyceride has 3 fatty acid tails. Everyone good there? That's how we store fat. Okay, next up, let's talk about steroids. Yeah, get swole, right? Steroids, actually not related to proteins, believe it or not. So steroids are lipids. Steroids are usually made out of 4 rings. 1, 2, 3, 4. Steroids, examples of steroids are testosterone, estrogen, androgens, cholesterol, all steroids. Steroids are hormones usually. So yeah, steroids are all lipid. And then lastly, we have our phospholipid. This is the most important one you have to know. Phospholipid, most important lipid. Make a special note of this one. Phospholipid. So it looks very similar to our triglyceride. What we're going to have is a glycerol group. We're going to have 2 fatty acid tails. We're going to have a phosphate group. And then we're going to have a head group, usually called choline. C-H-O-L-I-N-E. So here, we're going to swap out one of our fatty acid tails to instead bind with a phosphate group that has this choline. Now, what's unique about phospholipids? They have a unique property. They're amphipathic. What does amphipathic mean? Anyone know? They're both hydrophilic and hydrophobic. Thank you. Yeah. So phospholipids are both hydrophilic and hydrophobic. This is what all of our cell membranes are made of, right? All of our membranes are made of phospholipids. The reason is because the phospholipid head is hydrophilic. That means it likes interacting with water. It's able to interact with water. These tails are hydrophobic, meaning they don't like interacting with water. We have in our membranes what we call a phospholipid bilayer. Phospholipid, meaning that it is made of phospholipids. Bilayer, we have 2 layers of phospholipids sort of sequestering their nonpolar or their hydrophobic regions from water. So you see we make sort of this like sandwich almost in our cell membrane. It looks a little bit like this. This is a close-up of our phospholipid bilayer. All right. What kind of bonds do you think hold together our hydrophobic region of this phospholipid bilayer? Is water polar or nonpolar? Polar. Do polar things like other polar things, or do they like nonpolar things? They like other polar things. These are going to be nonpolar bonds. Hydrophobic equals nonpolar. Hydrophilic equals polar. So if something is hydrophobic, that means that it does not have any polarity in its bond. It's entirely nonpolar. Hydrophilic loves water. Philia, Greek word for love. Hydro, water, love of water. Polar. All right. That's going to be our phospholipid blurb. Everyone good on that? Okay. Let's talk a little bit about nucleic acids now. Nucleic acids. Oh, yes. You had an entire... Ooh, I'll raise my phone number. Yeah, okay. Nucleic acids. I'm going to erase all this phospholipid stuff. We had an entire unit on nucleic acids and DNA and all that fun stuff. It's fun to get back to the basics, though, don't you think? Nucleic acid. It's made of 3 things. I'm going to ask you what they are all made of. So we'll have this. What is this called? 5-carbon sugar. All nucleic acids have the same basic 3 components. All nucleic acids, monomer being nucleotide, right? So a monomer of our nucleic acid is a nucleotide, which I have drawn here. Nucleotide. This is our 5-carbon sugar. Every nucleotide has a 5-carbon sugar. You can count the carbons. There are 5 of them. I'll actually draw an oxygen up here because this is not a carbon. Count the carbons. 1, 2, 3, 4, 5. 5-carbon sugar. We have our nitrogenous base. It's just our base. Adenine, thymine, cytosine, guanine contains nitrogen, our nitrogenous base. This is the only thing that differs between our nucleotides. Sometimes uracil, if you want to get fancy, get an RNA, right? Remember uracil? Good. And then we have our phosphate. So we have a phosphate over here, 5-carbon sugar, 5S here, nitrogenous base, NB over here. Now there are also 2 carbons that you need to know about on our nucleic acids. We have our 5' carbon up here and our 3' carbon down here. These tell you the direction that DNA runs. How does DNA run? Begins with an A. Antiparallel. That means that 2 strands run in opposite directions, right? So we'll have 1 strand of DNA. These are going to be the bases sticking out to the side. This strand might run up. It might go in the up direction. We'll have a 2nd strand that binds to the bases of the 1st strand. This strand runs down. But you can't just say up and down in a cell, because in our cells, this is what our DNA looks like. Which way's up and which way's down, right? You can't tell. So instead we say 1 strand runs from 5' to 3', another strand runs 3' to 5'. Imagine if the 3' end were on top, this nucleotide would be upside down. To put this on top, you have to rotate this whole thing 180 degrees. That's how we say up and down. We say 5' to 3' or 3' to 5'. Okay, good. That's all I want to talk about nucleotides for now. We'll revisit them. And lastly, we have proteins. So proteins, what is the monomer of a protein? Amino acid. Yeah, everyone's quiet now. I like the energy before. We were on a roll. Yeah. Monomer of a protein is called an amino acid, AA. Polymer of a protein is called a polypeptide. What kind of bonds hold proteins together? Peptide bonds. That's right. Peptide bonds hold proteins together. Good. There are 4 levels of protein structure that you need to know about. Primary, secondary, tertiary, and quaternary. Luckily, they are all ordered in a way that makes them easy to remember. You know, primary first, secondary second, tertiary third, quaternary fourth. So, primary protein structure is going to consist solely of your amino acid polypeptide bonds. So we have these amino acids. They're all bound to each other via these peptide bonds. This is a peptide bond right here. What reaction makes peptide bonds again? Dehydration reaction, that's right. Good. So this is our primary level of protein. Is this a functional protein? No, that's right. Secondary level of protein. First I should define what structural protein or a functional protein is. A functional protein needs to have the correct blank and blank. Structure and sequence, that's right. So here we have a sequence. We have a sequence, but we don't have the right shape, right? Okay. Now, our secondary level of protein is where we start getting that shape, that right shape. So if your primary protein grows long enough, it'll start coiling into itself to make an alpha helix. This is an alpha helix, or it might make this sort of like crinkled cardboard shape called a beta pleated sheet. The bonds that hold these together are going to be peptide bonds, and then we also have hydrogen bonds between the amino acid backbone. So hydrogen bonds and the amino acid backbone will hold those together. Oh, I should probably draw out what an amino acid looks like. That might be helpful, right? So this is the general structure of an amino acid. I have a hydrogen here, and then the carboxyl. Okay, there we go. Then we'll have our R group. All right, this is the general structure of an amino acid right here. We have our N-terminus. N-terminus. We have our, also known as our amine group, our amino group, right? So actually, this is the amino group. Let's call this the amino group. I like that better. This is going to be our carboxyl group. We're going to have our C terminus, our N terminus. When we have these polypeptide bonds occur, what's going to happen is the N terminus and the C terminus are going to bind to each other. So if I were to elongate this amino acid, we'd undergo a dehydration reaction. We'd get rid of this OH, and we'd have an N over here, and then a C, H, R, and so forth. See what I'm doing here? So we can elongate like that. The N and the C termini bind to each other to elongate. Our R group is what makes our amino acid unique. What makes our amino acid unique? The R group. Yes, excitement. The R group makes our amino acids unique. All amino acids have everything in common except for the R group. When we have our secondary structure of amino acids, we have hydrogen bonds occurring between the backbone, between this hydrogen and this oxygen. Not to be confused with what we get in our tertiary structure amino acid. Are tertiary structure amino acids functional? Yes, yes they are, great. So tertiary structure is kind of a combination of secondary. We might have an alpha helix over here, and then a beta pleated sheet over here, and then another alpha helix over here. So we get this big amalgam of protein complexes, right? And there are a lot of bonds that hold together our tertiary structure proteins. We have our peptide bonds, right, still from primary. We have our hydrogen bonds in the backbone from our secondary. We have now hydrogen bonds in the R group in our tertiary. So first new bond, hydrogen bonds in the R group. This R group is basically like a substitute B sign. So we have different R groups, those make our amino acids different. We can have hydrogen bonding occurring in R groups in our tertiary structure. We also have our disulfide bridges, our disulfide bonds, right? Remember those? So those are just bonds between two sulfurs. And then we also have ionic bonds. So we have those ionic bonds that are also very helpful in maintaining our structure. And then we also have hydrophobic forces as well. So if you remember back to sickle cell, that's an example of a hydrophobic force causing a protein conformation change. So those are some forces that hold together our tertiary structure proteins. A lot of proteins stop here. They're functional, they go do their job. Some proteins, the extra proteins, they go on to become quaternary. Quaternary proteins are just amalgamations of a bunch of tertiary level proteins. So we might have this tertiary level protein over here, we might have another tertiary protein, another, and then a fourth. So you have a bunch of tertiary level proteins binding together with all the bonds mentioned in the tertiary proteins. So we don't have any new bonds in that quaternary structure. They all bind together to serve a very specialized purpose. An example of a quaternary protein is hemoglobin in your blood, used to carry oxygen. Pretty nifty, right? It's a big protein too. Okay, so that's going to be our macromolecules. Isn't it funny how much one little word contains, how much information? Okay, we got through one. All right, let's talk about prokaryotes versus eukaryotes now. What are we? We're eukaryotes, that's right. In my Tinder bio, I actually said that I was a professional eukaryote for a little bit. I didn't get many swipes, so I took it out. Yeah. So let's talk about some of the differences between prokaryotes and eukaryotes. Let me erase this. Okay, so which is larger, prokaryotes or eukaryotes? Eukaryotes. That's right. Good. Which one has more DNA? Eukaryotes have more DNA too, a little more unsure on that one. So we're just talking big differences here. That's not one of the big three. So eukaryotes are larger. Which one has membrane-bound organelles? Eukaryotes. Eukaryotes. Which one has a nucleoid? Prokaryotes, that's right. Three big differences between prokaryotes and eukaryotes. Eukaryotes are larger. Eukaryotes have membrane-bound organelles. Eukaryotes have a nucleus. Prokaryotes have a nucleoid. Membrane-bound organelles, that just means organelles that are made up of membranes. So you see a lot of membranes in our eukaryotic cells, right? We have our rough ER, we have our smooth ER, I'll talk about these in more detail. We have our Golgi apparatus. We have mitochondria. We might have some chloroplasts if we are a plant. We got a lot of membrane organelles inside of our eukaryotes. Prokaryotes don't have that. They have no membranes inside the cell. They just have that membrane on the outside. And then they have this little ball of DNA in the middle. That's the nucleoid. It's just a little free-floating region where DNA is located. So that's going to be some similarities and differences between prokaryotes and eukaryotes. Okay, next up, let's talk a little bit about the names and functions of the organelles. I just kind of mentioned them a little bit. So we're talking specifically about eukaryotes when we talk about organelles. Let's talk about some of them. Someone tell me their favorite organelle. What's your favorite? You got a favorite? I have a favorite. The Golgi apparatus. You work at UPS?
No.
No? No? Yeah, that's what it is. Golgi apparatus is going to be effectively the UPS of our cell. This is the Golgi apparatus, like right here. Looks like a stack of pancakes. It is involved in the transport of materials inside the cell. So if you want to send something somewhere, you send it to the Golgi apparatus. The Golgi apparatus packages it up and sends it to where it needs to go. If you have a protein that belongs in the nucleus, it will get sent to the Golgi apparatus, and the Golgi apparatus will send it to the nucleus. That's the big idea behind the Golgi apparatus. Everyone good there? Another organelle is going to be the endoplasmic reticulum. Big word, we just call it the ER, not the emergency room. Don't get that confused. So we have this ER, we have the rough ER and the smooth ER. What makes the rough ER rough? One word.
Ribosomes.
Wow, yes, ribosomes, good. So ribosomes make the rough ER rough. What do ribosomes make? One word. Proteins, that's right. So look, you just told yourselves what the function of the rough ER is. The rough ER makes proteins. It specifically recruits ribosomes to make membrane proteins. So how do you get all those membrane proteins in your cell's membrane? They're made in the rough ER and then shipped off to the cell membranes. So that's what our rough ER does. Our smooth ER is involved in a variety of activities depending on what type of cell you're in. So in the smooth ER, or excuse me, in the rough ER of every cell, you're always going to make proteins. In the smooth ER, you're going to do different things depending on where you are. Your muscle cells will use the smooth ER to store calcium, for example. So will your bones. Another function of the smooth ER, say in your liver, will be detoxification of compounds, right? That's another function of the smooth ER. Or lipid synthesis is also a function of the ER. That's where that occurs in some locations. So the smooth ER is very specialized. It depends where you are, but three big things it is involved in: calcium storage, detoxification, and synthesis of lipids. All right, everyone good there? Sweet. What other organelles do we have to talk about? The nucleus holds DNA, right? And then we have our mitochondria and our chloroplasts that we'll talk about later. So that's just a little bit about our organelles. Where are we? Oh, the cytoskeleton. The cytoskeleton, yes, the cytoskeleton is very important. The cytoskeleton is sort of what holds the cell's shape together. So you can imagine all here, we have a big skeleton kind of holding this ball in place. This is the cytoskeleton. The cytoskeleton is made of three parts. It is made of microtubules, microfilaments, and intermediate filaments. Anyone remember which is the strongest? Intermediate filaments are the strongest component of the cytoskeleton. Microtubules are made the fastest. Microtubules are what we use during mitosis and meiosis, right, to move things around. And then we also have our microfilaments, which are usually used in things like muscle contractions. So those are three pieces of the cytoskeleton. They all help maintain the cell's structure. They have other purposes too. So microtubules are also used for transport of material. How do things go from one part of the cell to another part of the cell? Does anybody have a marker, by the way? This one's kind of running low. No? Okay, yeah, thank you. Sorry about that. So this is a microtubule in a cell, right? We have these motor proteins that move along microtubules holding vesicles. So the microtubule sort of serves as a railroad for the transport of materials around the cell via vesicles. So this is a vesicle. A vesicle is, again, going to be a small pocket of membrane that holds something. It's kind of like a transport bubble that contains something. Can I borrow a marker? Ooh, a lot of colors here. Let's do blue. Thank you. Okay, I hope this marker works. It does, great. Okay, so now you all can see. That's the cytoskeleton. I don't want to talk too much more about that. We didn't go into too much detail. In 329, I'll go into more detail. Ooh, components of membranes. This is a fun one. Okay, so we know that our membranes are effectively made of our phospholipid bilayer, right? But what gives membranes their function? Those are going to be our proteins, right? So proteins give membranes function. Let's talk about some of the proteins that we might see in a membrane. So, you know, say we'll have our phospholipid bilayer over here, right? There are two major classes of proteins. They're called integral and peripheral proteins. So our integral proteins span the length of the membrane. They have one head poking out on the outside and another head poking out on the inside. Our peripheral proteins, so I'll label this as I, our peripheral proteins are only on one side of the membrane. They might be sticking out on the inside, but not the outside. They might be sticking out on the outside, but not the inside, or they might be lodged in the middle of the membrane. Effectively, peripheral proteins do not span the full length of the membrane. That's how you can remember that. Integral goes all the way through. Peripheral proteins do not go all the way through. Now, membranes are involved a lot in transport. So we need to talk about some transport proteins. So we have both active and passive forms of transport and transport proteins. Let's see. So one type of transport protein is going to be a channel membrane protein. Remember that. Channel protein is for molecules that cannot pass through membranes because they are charged. So in order to pass through our phospholipid bilayer, we need to get through that hydrophobic tail region, right? Remember we were talking about that region that is nonpolar, that doesn't like interacting with polar or charged things? If you have charged ions like sodium ions, Na+, those sodium ions can't go through this membrane because they don't want to interact with the nonpolar tails. We need then a channel protein. So we open up this channel protein. Sodium is able to interact with the polar interior of the channel protein and move into the cell. This is one example of transport. Now, when we talk about sodium transport into a cell, this is usually a type of passive transport. It's passive because we're going from high concentration to low concentration. This is a big idea that I want you all to hit on. So if you're falling asleep, I want you to wake up for this. So we have concentration gradients inside and outside all of our cells. As you can see, I'm drawing a lot of sodiums outside of this cell. Molecules of the same type, atoms, elements of the same type, they want to repel each other. They do not want to be in the same area together. We have a lot of sodiums on the outside of this cell. They want to get away from each other. They want to go from a high concentration of sodium to an area where the concentration of sodium is a little bit lower, like the inside of this cell. So when we open up this transport protein, this channel protein, the sodiums are going to naturally move down it. They're going to naturally go through it and go to the inside of the cell because the concentration of sodium is lower there and they want to spread out. That's called passive transport. Passive transport requires no energy and relies on that concentration gradient. Yeah.
Can you show us one of those examples where she had like those boxes and it said like 0.1 molar was on this side and like 0.4 was on the other, and like that?
Yeah, so that's with osmosis. I'm going to give you a really good example of osmosis. Right now, I'm building the structures of osmosis, though, the cognitive scaffolding process. I want you all first to understand this idea of going from high concentration to low concentration. Is everybody good there? Everyone understand that things want to go from high to low concentration? That's good. I like that. That's a good start. So when we have things going from high to low concentration, that's passive transport. It occurs naturally. Another type of passive transport relies on carrier proteins. So if you have something really big, like glucose that can't go through the membrane because it would destroy the membrane just by its sheer size, we have these carrier proteins. These carrier proteins just kind of open up like this V shape, wait for something to bind, and then when something binds to it, they invert and spit it out on the other side. You have a very high concentration of glucose. This glucose is going to go bind to the carrier site in this carrier protein. It's going to move into the carrier protein and then back out and inside of the cell. That's how carrier proteins work effectively. All right. Those are two forms of passive transport. You also want to be aware of active transport as well. Well, actually, I don't see active transport on here, so I'm not going to talk about it. Does that sound like a good idea? Yeah? Okay. If you have questions about active transport, talk to me later, but it looks like this is not on your study guide, so I don't want to mention it. I will talk about osmosis, however, and if you see active transport or passive transport on there, let me know. I don't see it. Osmosis. A lot of people miss this on the test. This will come back. You will see this in every biology and chemistry class that you have for the next year. So it's really a kind of simple concept. I want to make sure you all understand it. Osmosis has to do with the diffusion of water. Water, just like everything else, wants to move from areas of high concentration to low concentration. Now, when we talk about osmosis, or the movement of water from high to low, we have two things to consider. We have solute, S-O-L-U-T-E, or things that are not able to move across a membrane, and then we have the water. So as you can see here, I'm drawing these big stars and I have a semi-permeable membrane. The semi-permeable membrane means it lets some things through but not others. These big stars can't go across this membrane, but water can go across this membrane. So we have big stars surrounded by water on both sides of this sort of apparatus. On this left side, we might have a 30% solute concentration. On this right side, we might have, say, a 10% solute concentration. Now, if 30% of this is solute, the other 70% has to be water. If 10% of this is solute, the other 90% has to be water. Water is the only thing that can move here. Water wants to even itself out. Water wants to move from an area of high concentration to an area of low concentration. If you look at something like this, water is going to move from right to left to dilute the solute in this box here. Everyone kind of see that? Water is only concerned with moving from high concentration to low concentration. Inside cells, we see similar things. So if we have a little red blood cell and we drop it in an environment that is very high in concentration of water, let's say it's a 90% H2O solution, and the cell is only 70% H2O, water is going to move inside the cell because there's more water outside the cell, there's less inside. The water wants to even everything out. It moves from high concentration to low concentration. That causes the cell to swell up like a balloon and often lyse, L-Y-S-E. All right, that's an example of osmosis. Everyone feel kind of good about that? I don't anticipate Dr. Rabin asking about that on the test because it's not on her big review sheet here, but it's important for you all to know nonetheless, and it could be on there. You never know. Okay, so now let's talk a little bit about, yes, this is a really big concept that you all need to know. So cellular energetics, very, very important concept. Anabolic, catabolic, endergonic, exergonic. Does all that sound familiar? So we need to know a little primer about metabolic processes before we jump into mitochondria reactions and chloroplast interactions. So there are two laws of thermodynamics that you need to know. What is the first law of thermodynamics? Anybody remember? Energy is not created or destroyed, ever. First law of thermodynamics. It only changes shape. That one's pretty easy, right? Now, the second law is where people usually get thrown off. The second law states that the universe is constantly moving towards this state called entropy. E-N-T-R-O-P-Y. Now, entropy is kind of like the universe's natural state of disorder. Remember how I said everything wants to spread out? All those sodium ions want to spread out right from each other. Everything in the universe is trying to spread out. It's trying to avoid other molecules. Entropy is this natural urge for molecules to spread out over time. If I, what's a good gas? Hydrogen chloride. That's a very deadly gas. If I have a bottle of hydrogen chloride over here and I open it, the gas is not going to stay in the bottle. The gas is going to release from the bottle and fill the room. All those molecules want to spread out from each other, and we would all die. I would not do that, of course, because that'd be terrible. Yes, so everything in the universe is trying to spread out. That's the idea behind entropy. Now, where am I going with this? Oh, yeah. This ties into our reactions. So reactions that increase entropy are what we call energetically favorable. Now, the reaction of glucose into carbon dioxide is moving very highly ordered molecules, a big glucose molecule, right, to a bunch of very small carbon dioxide gas molecules. This is a very energetically favorable process. Think about it. All of those carbons in glucose, all very close together, all tightly bound, right? Versus a lot of little carbon dioxides able to freely go wherever they want, spread out, much smaller molecules. This is an energetically favorable reaction because this increases the entropy of the system. Does that idea kind of make sense? Okay, so I want you to keep this in mind when we talk about all of these cellular energetics. Now, there are two major types of reactions in biology, and they're called catabolic and anabolic. So we have catabolic, and we have anabolic. Which one of these increases entropy? Catabolic, that's right. So catabolic increases entropy. That means it's energetically favorable. That means it naturally wants to happen. So catabolic increases entropy. What's another way to say it's energetically favorable? Somebody tell me. Negative delta G. Negative delta G. So one way we can say something is energetically favorable is we can say it has a negative delta G or a Gibbs free energy value that is negative. So this graph that I drew right here, this is an energy graph. This is a Gibbs free energy graph. We start with a lot of potential energy. We go from this highly energized, highly ordered molecule to a much less ordered molecule, to a much less energized molecule. You know, all of these complex bonds, they have a lot of energy in them that are released when they're broken. So when we go from high energy to low energy, we say this is a negative value, and we say it is a delta G value. Delta, change, G, energy. We have a negative change in energy. That's going to be very favorable. We're going from very ordered to very not ordered. Catabolic entropy, negative delta G, that means that it happens naturally. What's another way that we can say a reaction happens naturally on its own in nature? Spontaneous, that's right. We say this is a spontaneous reaction. Okay, good, I like that. So an example of a catabolic reaction would be everything that happens in your mitochondria, right? Taking glucose, turning it into carbon dioxide. This is a catabolic reaction. Taking something very highly ordered, breaking it up into much less ordered molecules. Okay. That's catabolic. Anabolic is the opposite. Anabolic decreases entropy. It has a positive delta G value, and it is what we call non-spontaneous. How do we make a non-spontaneous reaction happen, though? Energy coupling, yes, somebody said it. I'm so glad. Energy coupling, that's right. So we know when we break things up, we get a negative delta G value, we get a release of energy. We can use that energy then to power other reactions. So our most famous form of energy coupling is ATP, right? Let's say we want to use, let's say we want to make, say, a carbon-carbon bond. We want to turn two carbon dioxides into this carbon-carbon bond. Is this catabolic or anabolic? Anabolic, that's right. We're taking two separate molecules and we're combining them. We're making something more ordered. You could say that whenever we make a polymer, whenever we go from monomer to polymer, that's anabolic as well. Whenever we undergo a dehydration reaction, that's anabolic because we're lengthening, we're making it bigger, right? So if we want to do this, we could say this has a delta G of positive 5. This will never happen in nature. You will never see this happen isolated in nature. You can use energy coupling, though, to make this happen. So if we combine this reaction with this reaction, going from ATP to ADP plus phosphate, this has a delta G of negative 7.4. If we do both of these reactions at the same time, we can add up both of the delta G's, and we can see that the overall change is going to be negative. It will be negative 2.4. Everyone see what I did there? So we can combine chemical reactions to make these non-spontaneous reactions happen. Combine a catabolic reaction with an anabolic reaction, and you can make these non-energetically favorable things occur. Everyone have that down? This is why ATP is such a great energy molecule, because it's very easy to make. You have a lot of it, and you can recycle it, and you can use multiple ATPs to power one reaction. Any questions about energy coupling? Super important. I love metabolic things. Okay, so next up, we're going to talk a little bit about cellular respiration. Okay. This is, question?
So you said that you combine non-spontaneous reactions to make spontaneous reactions happen?
You combine spontaneous reactions with non-spontaneous reactions. So if I want to go from two little molecules to one big molecule, if I want, let me see what my marker is actually. Great example. If I want to do this, I have two markers. If I want to make this happen, that took energy. I had to put some force in this to make this happen. This will never happen in nature. If I have these two markers sit here, they will never, ever combine like that. If I have two molecules sitting next to each other, they're never going to combine. If I couple that with a reaction that is catabolic, though, if I break this down, this provides energy to make this bond occur. That kind of makes sense. So if you couple those reactions, then you're able to get the combination of bonds. That is your question? Yes. Excellent, yes. Also, I encourage questions because I am just flying. I am already at Unit 2, and we did not even get to our break yet. Break will be at 5:30, by the way. So we'll take a little 10-minute break. So stick with me. I'm going to fly through cellular respiration like it is nobody's business. I'm going to erase this too. So is cellular respiration, mitochondria stuff, is that a catabolic or anabolic reaction? Catabolic. It's catabolic. We're ultimately breaking things down. The overall delta G is negative. So cellular respiration, let's talk about the formula for it. Now, you need to know big picture stuff, but you also need to be aware of the little details too. So I'm going to walk through the big picture stuff while keeping in mind the little details. So cellular respiration, the overall formula, what do you start with in cellular respiration? Glucose, that's right. C6H12O6. What else do you start with in cellular respiration? Oxygen, that's right. This is why we need to breathe. This is why we're aerobic. Oxygen consumers. And what do we get out of this? What's one thing we get from this reaction? We get water. That's one thing that we get. H2O. We get 6 H2O. What's another thing that we get? We get 6 carbon dioxides. And then what else do we get? ATP. Lots of ATP. We get 30 to 32 ATP. Tons of ATP. Good. Okay, so let's talk about where this actually happens. We talked about the overall reaction. So first of all, this is going to happen in eukaryotic cells with the mitochondria. So we'll draw our eukaryote. We have, say our nucleus. We'll have our ER. We'll have our Golgi. And then we're going to have our mitochondria over here. So we are here in this mitochondria. We're going to start where in cellular respiration? So we have a glucose. We're going to start with glucose. Where are we going to put our glucose for the first reaction? The cytoplasm. We're going to take our glucose to the cytoplasm, which is just kind of like the liquid matrix inside the cell. And we're going to go through what reaction? It begins with a G. Glycolysis. True or false? Every living organism can go through glycolysis. True, that's right. Even prokaryotes. Can prokaryotes go through the rest of cellular respiration? No. Good. So we have glycolysis. So in glycolysis, we put in a glucose, and we're going to get out 2 ATP. We're going to get out 2 pyruvate. We're going to get out 2 NADH molecules. Okay, so now we take our pyruvate and we move it into the mitochondria. So we go in mitochondria to do what? What? Good, yes, pyruvate oxidation, excellent. So next up, we move into the mitochondria. We undergo pyruvate oxidation. We get 2 acetyl-CoA. We get 2 carbon dioxides, and we get 2 ATP molecules. Oh wait, no, we don't. Sorry, we get 2 NADH molecules. Slip of the tongue there. Getting a little ahead of myself. This is our pyruvate oxidation process. This preps our pyruvate to enter the citric acid cycle, also known as the Krebs cycle, also known as the tricarboxylic acid cycle. Yeah, so now we have our acetyl-CoA. We're ready to move to the mitochondrial matrix. In matrix, the matrix of the mitochondria is the very, very middle. So we're in the very middle of our mitochondria now in the matrix. And we're going to go through the citric acid cycle. Now, the citric acid cycle is going to squeeze the energy out of the acetyl-CoA and make a bunch of other molecules. We're going to get 4 carbon dioxides. We're going to get 6 NADH molecules. We're going to get 2 FADH2 molecules. And we're going to get 2 ATP molecules. Okay. This is the overall process of cellular respiration. Dr. Rabin is going to ask you, where's the energy? She wants to know where all of the energy is contained in every step of this process. So let's walk through it. First step, the energy is in glucose, right? Where is most of our energy after glycolysis? What molecule?
Pyruvate.
Pyruvate, good. So we remove a little bit of energy in the form of ATP and NADH. Most of our energy is still in pyruvate. We come over here to pyruvate oxidation. Where is most of our energy contained after that? Acetyl-CoA, that's right. We lose a little bit more energy in the form of NADH and carbon dioxide. We move to the matrix. Now where is our energy stored? Electron carriers, that's right. So the big idea, the big picture behind cellular respiration up until this point, all the way up to the citric acid cycle, everything we've done up until now, the purpose is to take the energy from glucose and put it on these electron-carrying molecules. So NADH and FADH2 are electron-carrying molecules. Electrons are energy, right? We're taking that energy from glucose and we're putting it on these electron-carrying molecules. So that's everything that we've done up until this point. Our goal is to put all that energy on these electron carriers. Now let's see what we have going in to the electron transport chain. So we have total 6 CO2. We have 10 NADH. We have 2 FADH2. And we have 4 ATP. This is everything that we have up until this point. How do I figure that? Well, we start with glucose. We consume it. We go to pyruvate. We consume that. We go to acetyl-CoA. We consume that. Everything left over, I just added it all up, and that's what I just wrote over there. So we just added all this stuff up. This is the total of everything that I have circled, everything that we have going into the electron transport chain. Okay, so let's do a little diagram of our mitochondria. Let's talk about where we are right now. So, big zoomed in view of our mitochondria, right? The citric acid cycle occurs in the matrix. The CAC occurs in the matrix, or the middle. That means all of our products, most of our products are in the matrix. Our electron transport chain is going to take place on the inner membrane folds, also called cristae. So these folds of the inner membrane are called cristae. With that in mind, let's draw out what this process looks like. And this is where we get the energy. This is where we make the ATP. This is where we convert that electron energy, that redox energy, into ATP, chemical energy. Okay. So we're going to have a lot of proteins. We're going to have a lot of protein complexes. We're going to have 1, 2, 3. Well, this should be sort of like a different shape. 3, 4. And then we're going to have something that looks a little bit like this. I'll draw it over here. Ooh, I love how big this whiteboard is. This is really wonderful. I wish I had this in my regular. I'm drawing a phospholipid membrane. Use your imagination. You all can imagine the phospholipids, right? I hope so. And then, okay, good. Then we'll have, say, this. We'll have this. So this will be our complex 1. We'll have our complex 2 over here. We'll have our ubiquinone over here. We'll have our complex 3, complex 4. Okay. And then site C, and then this will be our ATP synthase. This is where things get a little bit crazy, so I want you to follow along. Okay. Can the live streamer see? Sort of. All right, we're going on adventure live streamers. Okay. See how I look out for everybody? Okay, so we have our NADH molecules in the matrix still, NADH, and we have our FADH2 molecules in the matrix still too, FADH2. So what's going to happen is these NADH and FADH2 molecules are going to give up their electrons. NADH is going to turn into NAD plus 2 electrons plus a hydrogen ion. So we make a little hydrogen ion over here. We make these 2 electrons. Now FADH2 is going to do something similar. It'll just turn into FAD and 2 electrons and 2 hydrogens. So FAD plus 2 hydrogen ions plus 2 electrons. These electrons are going to go from NADH anyways. The electrons from NADH are going to move up complex 1. And when these electrons move across complex 1, they're going to cause complex 1 to sort of twitch almost. And when complex 1 twitches, it's going to suck up hydrogen ions from the matrix and push them outside of the matrix into the intermembrane space. So if we look at our diagram of the mitochondria, we're moving things from the matrix to the intermembrane space. We're sucking those hydrogens out and we're pushing a lot of these hydrogens into this intermembrane space. The electron is going to be carried by ubiquinol across to complex 3. Complex 3 is also going to push hydrogen molecules across this membrane. We're going to move to complex 4. The electron is then still going to push hydrogen ions across this membrane. So in the electron transport chain, big picture, what are we doing? We're moving electrons across proteins and shoving hydrogen ions in this intermembrane space. So when we move all of these electrons through here, we're going to have a very high concentration of hydrogen ions in the intermembrane space. Now, if you remember what I said about transport of sodium ions, right, which is why I told you all to wake up at that time, things don't like being in high concentration near each other. These hydrogen ions, there are a ton of them, they don't want to be near each other. They want to separate. They want to spread out because there's a high concentration, and they also want to spread out because there's a very high positive charge in the area. Think about it. You have a bunch of positive ions, right? A lot of positivity. Positive things repel each other. These hydrogen ions are repelling each other because they're all positive, and they're also repelling each other because they're in very high concentration. So when we move these electrons across these membrane proteins and we're shoving all these hydrogens across, we're creating a very strong, what we call chemiosmotic gradient. Chemiosmotic, C-H-E-M-I, osmotic, gradient. That chemiosmotic gradient relies on 2 parts. It relies on a concentration component and a charge component. That's going to be what makes up our chemiosmotic gradient. Now, this electron, when it's done in complex 4, it has to go somewhere, right? You can't just have a buildup of electrons in complex 4. So what's going to end up happening is this electron is going to move off of complex 4, and it's going to move and attach itself to a free-floating oxygen molecule. So this oxygen molecule is actually going to take 2 electrons. It'll become oxygen 2 minus. 2 hydrogen ions floating around are going to go, hey, we like that negative charge. They're going to combine, and you're going to make 1 neutrally charged H2O per cycle. So you're going to end up getting 6 H2Os from this process. So this is how we make our water. Oxygen is the final electron acceptor in this electron transport chain. Now, Dr. Rabin, as I'm sure many of you have found out, may not necessarily ask you that directly. She might not directly ask you, what is the final electron acceptor in the electron transport chain? I have a strong feeling all of you will go oxygen. She could instead ask you something like, what would happen if humans stopped breathing oxygen? What happens if you are suffocating, you don't have access to oxygen? How would that affect your cells? Why would you die? The answer to that is you would not be able to move electrons onto your final electron acceptor. You would not be able to continue this process. When you're starved of ATP, your cells will not be able to continue their activities. When you deprive your brain of ATP, it can't go about its normal functions. It will shut down. Does that kind of make sense? Everyone understand like the trick questions she can ask that way? So you need to know the facts, right? But you also need to be able to think critically and apply the facts. And that's the part that's kind of hard for me to explain because there are a million ways you can approach that. But if you know the facts and think about what you know, then you should be fine. Question? Huh? Oh, great question. Yeah. So complex 2 takes FADH2 electrons. So notice how NADH follows this pathway, right? If we were to use FADH2, it would look a little something. It would look a little something like this. Let me come over here. FADH2's electrons are going to move through complex 2 to complex 3 to complex 4. So you can see that they sort of follow different paths almost. So the complexes still do the same things. Complex 2 doesn't pump energy, or it doesn't pump hydrogen ions across the membrane, but you don't need to know that. So yes. Now, how do we make energy from this? Alex, how do we make energy? Big picture, we just shoved all these hydrogens on the side of the membrane. How do we get ATP? Well, these hydrogen ions that want to desperately get out, they have one way out. Only one way out of this big mess, this big hodgepodge crowded area, through ATP synthase. So these hydrogen ions are able to come back inside the matrix where there are no hydrogen ions, where it's nice and free and wonderful. It's like, you know, the vacation spot. It's like the Atlantis Hotel of the mitochondria matrix. When these hydrogen ions move down ATP synthase, they power the rotation of ATP synthase, which then creates ATP molecules. So what you want to know is that these hydrogen ions, when they're moving down this gradient, they are producing energy. And that energy is being used to power the creation of ATP. If that sounds a little abstract, that's because it is. Come talk to me in 329, and I'll talk more about how this specifically works, which you all will have me in 329 if you are staying on your course. I'll see you all in a year. But anyways, so ATP synthase, hydrogens move down the ATP synthase. That's how we make our ATP. And we make a lot of ATP from this. How much ATP do we make from this? 26 to 28 ATP. We make a majority of our ATP here. And then we have our other 4 from our reactions up through the citric acid cycle, and that's how we get our 30 to 32 ATP. Okay, where do the electrons come from in this transport chain? What donates the electrons? Electron carriers, NADH, FADH2. Where do they go? Where do they end up? Oxygen. They're put on oxygen. That's our final electron acceptor. Oxygen then turns into water. How is the energy made? What makes the energy? ATP synthase makes the energy. How does ATP synthase make the energy? Hydrogens move down it. Hydrogens move down their concentration gradient through ATP synthase. That produces energy. Those are some questions that I want you all to take away from this. Some answers to those questions specifically. Are we good? Okay, good. I'll move our live streamers back over here. Or maybe this will be you at the library in a couple hours. Then I moved over there. Okay, so that's going to be our cellular respiration. Ooh, let's talk about fermentation really quick. So, and then after we talk about fermentation, we can take our little break. Does that sound good? We like that idea? Yes. Yes, okay, good. And then we'll jump right back in with photosynthesis. So, can I erase all this? I'm gonna erase all this. All right. Ooh, it's a little hot in here, don't you think? I was wearing jeans earlier, but I made the strategic decision to put basketball shorts on under my jeans in case I wanted to take them off, because it was just too hot. It's all about thinking ahead when you're going to be at the library for 8 hours after this. Okay, let's talk about fermentation really quick. Fermentation is something that occurs in both prokaryotes and eukaryotes. And does anybody know the purpose of fermentation? What's the big purpose of fermentation? Yeah. Oh, sure. To create NAD plus, even bigger picture, why do you want to create NAD plus? To keep going through glycolysis. The purpose of fermentation is to allow the cell to keep going through glycolysis. Purpose of fermentation keeps you going through glycolysis, right? So when we go through glycolysis, we take glucose, we take actually this molecule called NAD plus, and we convert these into pyruvate, NADH, and of course our ATP, our 2 ATP. So we want this ATP. If we are a bacterial organism that has no cellular respiration process, glycolysis is the only way you can get energy. Glycolysis is very fast, and it produces a very small amount of ATP, but if you go through it quick enough, you can build up a lot. It's kind of like if I went over to Olivia and I said, every time you click your pen, I'll give you $2. It's a great deal, right? I bet you'd be clicking your pen 10,000 times a day. You'd be making a lot of money. That's what like glycolysis is. The problem is though, whenever you go through glycolysis, you make NADH and you make pyruvate. These are things that we need to deal with, things that we need to get rid of to reset glycolysis. If I told you every time you click your pen, you gotta bring out 2 giant garbage bags to the dumpster, take a lot longer, right? It's kind of what we're using fermentation for. So what we do during fermentation, we take our pyruvate. This is the reaction of fermentation, the big picture. We take our NADH. We convert our pyruvate into either ethanol or lactic acid. And we convert our NADH into NAD+. What does that do? Let's talk about what that does. So we reset our NADH to make more NAD+. We need NAD+ to go through glycolysis. If we use up all of our NAD+ to make NADH, we can't do glycolysis anymore. We want to make sure we have a lot of this NAD+ so we can constantly be doing glycolysis, right? We take our pyruvate, we convert it into something more manageable, something easier to deal with. Ethanol, if you're in alcoholic fermentation, or lactic acid, if you're in a muscle cell. lactic acid fermentation. We can export these products a lot quicker or break them down or combine them into different things. So we're dealing with our pyruvate and our NADH, things that we don't want. We want an ATP from glycolysis. We got to deal with these other two things to keep that ATP production up. Does that idea kind of make sense? We good on that? Okay. So what I'm going to do now, well, hold on. Let me think about the timing here. So 5:20, 6:20. Yeah, we should be good. So let's take a little 10-minute break, and then we're going to come back, and we're going to talk about photosynthesis. All right, we'll break now.